Welcome, everyone. I'm excited to kick off our presentation today. The topic is polynomials. On this first slide, you'll see the title, Polynomials, and a brief overview of what we'll explore. We'll look at what polynomials are, how they work, and why they're important in mathematics. So let's get started and dive into the fascinating world of polynomials. Let's dive into some specific examples and case studies related to polynomials. On this slide, we see references to different cases, such as case I, case II, and case III, which explore various scenarios involving the degree and zeros of polynomials. We'll examine how the zeros relate to the coefficients in quadratic, cubic, and linear polynomials, highlighting their geometric meanings as well. Understanding the number of zeros a polynomial can have, along with their nature, helps us grasp the broader concepts of polynomial behavior. Additionally, we'll explore the division algorithm for polynomials, which is fundamental in algebraic manipulations. Overall, these examples and cases are designed to deepen our understanding of the structure and properties of polynomials, connecting their algebraic form to their geometric and analytical interpretations. Let's take a closer look at an example of a polynomial. We have p, x equals 2x squared plus x plus 3, and p, y equals 6y cubed minus 3y plus 5. These expressions are perfect illustrations of what a polynomial looks like. In mathematics, a polynomial is essentially an expression of finite length, meaning it has a limited number of terms. It's constructed using variables and constants, and importantly, the exponents on those variables are non-negative whole numbers. Understanding this is fundamental because polynomials form the backbone of many algebraic concepts we'll explore, and recognizing their structure helps us analyze their behavior and properties. So, as we proceed, keep in mind how these examples connect to the broader themes of algebra and functions. Let's take a look at this example. P, x equals 17x9 plus 4x7 3x4 plus 2x2 10. When writing a polynomial, it's important to always start with the term that has the highest exponent and then list the remaining terms in order of decreasing powers. This helps keep the polynomial organized and easier to understand. For instance, if we look at a polynomial like 7x5 9x2 plus 1, notice how the terms are ordered from the highest degree to the lowest. Now, polynomials can vary in the number of terms they have. We call a polynomial with 3 terms a trinomial, like 3x6 plus 13x5 if there are 2 terms. We call it a binomial, such as 4x3 or simply a constant like 7. And if it's just 1 term, we refer to it as a monomial. Recognizing these types helps us understand the structure of different polynomials and how to work with them effectively. Now let's talk about the degree of a polynomial. The degree is essentially the highest power of the variable in the polynomial. For example, if we look at the polynomial minus 8x7 plus 4x3 9x plus 5, the highest exponent here is 7, so the degree of this polynomial is 7. Similarly, for 5x6 plus x4 2x3 plus 9, the highest exponent is 6, making its degree 6. It's important to understand that the degree of a polynomial is determined by the term with the largest exponent, and this is what we call the order of the polynomial as well. Recognizing the degree helps us understand the polynomial's behavior and how it might look graphically. So, whenever you're analyzing a polynomial, always look for the term with the highest exponent. It reveals the degree and gives you insight into the polynomial's overall characteristics. Let's see how we can check whether a number is a zero of a polynomial. For example, take the polynomial p of x equals 2x plus 3. To check if minus 3, 2 is a zero, we replace x with minus 3, 2 in p, x. So, p of minus 3, 2 equals 2 times minus 3, 2 plus 3. When we simplify that, 2 times minus 3, 2 gives us, and then adding 3 results in 0. This confirms that p of minus 3, 2 equals 0. Therefore, the zero of the polynomial p, x, equals 2x plus 3 is equals minus 3, 2. Now let's consider a typical question. Find the zero of the polynomial p, x equals 2x plus 3. To do this, we set p, x equal to 0, so 2x plus 3 equals 0. Subtract 3 from both sides and we get 2x equals. Dividing both sides by 2, we find equals minus 3, 2. And this brings us to an important concept. The zero of a polynomial is that particular value of where the polynomial's value becomes 0. In other words, a real number k is a zero of the polynomial p, x, if p, k equals 0. Understanding the zeros of a polynomial is fundamental because it helps us analyze the behavior of the polynomial and find its roots, which are essential in many areas of algebra and beyond. Let's talk about the number of zeros a polynomial can have. For a cubic polynomial, which is a degree 3 polynomial, the graph can intersect the x-axis at up to 3 points. This means it can have a maximum of 3 zeros. Moving on to quadratics, or degree 2 polynomials, their graphs can intersect the x-axis at most twice, so they can have up to 2 zeros. Finally, for linear polynomials, which are degree 1, the graph can only intersect the x-axis at 1 point, so they have at most 1 zero. Understanding these maximums helps us see how the degree of a polynomial influences its roots and the shape of its graph, tying back to the overall theme of analyzing polynomial functions. Let's explore the geometrical meaning of zeros of a polynomial. Essentially, these zeros are the points where the graph of the polynomial crosses or touches the x-axis. In other words, if you look at the graph and see where it intersects the x-axis, those points correspond to the zeros of the polynomial. Now, if the graph of a polynomial p, x, intersects the x-axis at a point k, then we say that k is a zero of the polynomial. This is important because it connects the algebraic concept of solutions to the graph's visual behavior. When we consider a quadratic polynomial, like x2 plus bx plus c, its graph can take on 3 different shapes or cases. Depending on the coefficients and the discriminant, the parabola may intersect the x-axis at 2 points, touch it at 1 point, or not intersect at all. These cases help us understand the relationship between the polynomial's algebraic zeros and the graphical behavior. Understanding these concepts is key because it bridges the algebraic solutions with the geometric interpretation, giving us a clearer picture of how polynomials behave graphically. Here, the graph cuts the x-axis at 2 distinct points A and A. Now, this is quite significant because it shows us that the function crosses the x-axis twice, indicating there are 2 roots or solutions in this case. When we talk about these points, A and A, we're essentially identifying where the graph touches or crosses 0. This relates directly to the overall theme of understanding how functions behave and how their roots are located. In particular, recognizing multiple crossing points helps us analyze the nature of the solutions and the shape of the graph. So, in summary, this slide highlights the importance of these intersection points and sets the stage for exploring different cases based on how many times the graph intersects the x-axis. Here, the graph cuts the x-axis at exactly 1 point. This indicates that the quadratic function touches the x-axis just once, meaning it has a single real root. This is a key feature of case II. In this scenario, the discriminant of the quadratic is 0. As a result, the parabola is tangent to the x-axis, and the vertex lies exactly on the axis. This case helps us understand situations where the quadratic has a repeated root. Recognizing this pattern is important because it tells us about the nature of the solutions and how the graph behaves. So, in essence, when the graph touches the x-axis at only 1 point, we're dealing with a perfect square trinomial. This concept ties into the overall theme of analyzing quadratic functions through their graphs and roots. Now, in this case, the graph is either completely above the x-axis or completely below the x-axis. This situation is what we call case III. When the graph stays entirely on one side of the x-axis, it indicates a specific behavior in the function. For example, if it's above the x-axis the whole time, the function remains positive across this interval. Conversely, if it's below, then the function stays negative. Recognizing this pattern is important because it tells us that the function does not cross the x-axis at all within this interval. This has implications for understanding the function's roots and overall behavior. So, in essence, Case III helps us identify regions where the function maintains a consistent sign, which is a key aspect in analyzing and interpreting functions in calculus. Now, let's move on to the key relationship between zeros and coefficients of a linear polynomial. Remember, the general form of a linear polynomial is p, x equals x plus b, where it is not equal to 0. If we find the zero of this polynomial, which we call alpha, there's a simple formula to relate it to the coefficients. Specifically, the zero alpha equals negative b divided by it. This means that the zero is directly connected to the ratio of the constant term to the coefficient of x. For example, if b is 4 and a is 3, then the zero alpha is over a, which is minus 4 divided by 3. So, in this case, the zero of the polynomial 3x plus 4 is minus 4, 3. Understanding this relationship helps us see how the coefficients determine where the polynomial crosses the x-axis. It's a fundamental concept that links the algebraic form to the graph's behavior. Overall, recognizing this relationship makes solving for zeros more straightforward and connects the coefficients to the roots of the polynomial. Let's take a closer look at the general form of a quadratic polynomial, which is x2 plus bx plus c, where it is not equal to 0. This form is fundamental because it covers all quadratic equations. Now, suppose this quadratic polynomial p, x, has two zeros, which we'll call alpha and beta. These zeros are the values of that make the polynomial equal to 0. Understanding the relationship between these zeros and the coefficients, a b, and c is key to grasping the behavior of quadratic functions. Throughout this presentation, we'll see how the sum and product of these zeros relate directly to the coefficients, revealing a beautiful symmetry. This connection helps us solve quadratics more efficiently and deepens our understanding of their graph and roots. So, recognizing these relationships is a crucial part of mastering quadratic polynomials and their properties. So, from this slide, we're seeing that the sum of the zeros of the polynomial p, x, equals negative 3/4, and the product of the zeros is 1/2. Now, these are derived from the coefficients of the quadratic, specifically using the relationships over a for the sum and c over a for the product. In our case, since p, x, equals 4x squared plus 3x plus 2, the values are equals 4, b equals 3, and c equals 2. Therefore, the sum of the zeros, alpha plus beta, is negative b over a, which simplifies to negative 3 over 4. And the product, alpha times beta, is c over a, which simplifies to 2 over 4, and that reduces further to 1/2. This example highlights a key point. For any quadratic polynomial, the sum and product of the zeros are directly related to the coefficients. Remember, the sum is always negative b over a, and the product is c over a. This connection is fundamental in understanding how the roots relate to the polynomial itself. Now, let's delve into the relationship between the zeros and coefficients of a cubic polynomial. Remember, the general form of a cubic polynomial is x3 plus bx2 plus cx plus d, where it is not equal to 0. This means we're dealing with a degree 3 polynomial, which has 3 roots or zeros. These zeros are the values of that make the polynomial equal to 0. What's fascinating is how these roots are connected to the coefficients a, b, c, and d. For example, the sum of the zeros relates to the coefficient b, and the product of the zeros relates to the constant term d. These relationships are essential because they allow us to understand the roots better just by looking at the coefficients, and vice versa. This connection is a key part of polynomial theory and helps us analyze and solve cubic equations more effectively. So, understanding these relationships not only deepens our grasp of the polynomial's structure, but also ties into the broader theme of how coefficients reflect the roots of the polynomial. In summary, the division of polynomials follows a pattern similar to basic arithmetic. When we divide a polynomial f, x, by another polynomial g, x, the result can be expressed as fx equals g, x times a quotient q, x, plus a remainder r, x. This is similar to how we think of division with integers. Dividend equals divisor times quotient plus remainder. Now, an important point here is that if the degree of f(x) is greater than the degree of g(x), and g(x) is not 0, then there are unique polynomials qx and rx that satisfy this equation. The key is that the degree of the remainder rx is either 0 or less than the degree of gx. This concept is fundamental because it guarantees that every polynomial division yields a unique quotient and remainder, giving us a systematic way to break down complex polynomial expressions. So, the division algorithm for polynomials, which we've discussed, is a powerful tool that builds directly on these ideas, ensuring consistency and predictability in polynomial division. Now, by equating each of these factors to 0, we will get 1, -1, and 3. So all three zeros of the cubic polynomial are now known to be 1, -1, and 3. Next, you could find the factors of x squared minus 2x minus 3 by splitting the middle term as x plus 1 times x minus 3. This gives you x cubed minus 3x squared minus plus 3 equals x minus 1 times squared minus 2x minus 3, which factors further to x minus 1 times x plus 1 times x minus 3. Consider the cubic polynomial x cubed minus 3x squared minus plus 3. If one of its zeros is 1, then x minus 1 is a factor of this polynomial. So you can divide x cubed minus 3x squared minus plus 3 by x minus 1, and you will get x squared minus 2x minus 3 as the quotient.